Welcome to the second presentation. Second chairs will be Professor Kazım Şahin and Professor Amin Alizadeh. In this session, we have three presentations. First of all, Professor Reşat Apak from Istanbul Technical University. I would like to welcome Professor Amin Alizadeh as a chair for this session. Thank you.
Okay, I am opening this session. First speaker is Professor Reşat Apak. Reşat Apak, a member of Istanbul University. He received Master Science degree in Chemical Engineering from Istanbul University, postgraduate diploma in Marine Pollution from Liverpool University, obtained PhD, and Professor of Analytical Chemistry in Istanbul University. Professor Apak is a member of the principal member of Turkish Academy of Science, and also Academic Council member of TÜBA. He will present the food antioxidant, their impacts and determination. Okay, please.
Thank you. Dear distinguished guests of Asian Academy of Sciences and Turkish Academy of Sciences, I wish to especially thank Professor Nami Kemal Aras and Professor Kazım Şahin for inviting me here. For about 10 years or more, we have been working on food antioxidants and their determination methods, and the title of my talk will be Food Antioxidants, Their Importance and Their Determination. What are the two natural wealths of Turkey? First, Turkey is rich in fauna and flora in terms of plants and wildlife, 4 climates, fertile land, and rich variety of food plants. It also has a rich history reflected in the remnants of ancient civilizations everywhere throughout Anatolia. In fact, the second wealth is an indirect consequence of the first. If we think of the answer to the first question, why has this land attracted many civilizations over thousands of years? So, of course, that is why we have a very rich fauna and flora, and we can nourish all the people, all the civilizations that has passed through these lands, through Anatolia. And being an analytical chemist, that is why I and my group have engaged in antioxidants and their determination in plant extracts and food extracts. What is an antioxidant? An antioxidant may be defined as any substance that when present at low concentrations compared with those of the oxidizable substrate, significantly delays or inhibits oxidation of that substrate. That definition has been given by Halliwell and Guttridge, the famous anti-radical scientists of the world. Antioxidants play an important role in food preservation by inhibiting oxidation processes and contributing to health promotion rendered by many dietary supplements, nutraceuticals, and functional food ingredients. The mechanism of antioxidant action can be seen in this diagram. Here we see an antioxidant which donates an electron or an hydrogen atom to a free radical species, and the free radical species has unpaired electrons in its valence shell. But when the antioxidant donates an electron to this free radical or reactive species, then of course it is quenched because its electrons are paired in the valence shell. What are these species, reactive species? Especially reactive oxygen and nitrogen species, like superoxide anion radical, hydroxyl radical, hydrogen peroxide, some peroxyl radicals as well, and some nitrogen species such as peroxynitrite and hypochlorous acid perhaps. There are many species, and therefore these antioxidants sacrificially donate electrons and hydrogen atoms to these species in order to quench these species and thereby prevent some oxidative stress-originated diseases like cardiovascular disease, neurodegenerative diseases, and cancer, some types of cancer. For convenience, antioxidants have been traditionally divided into two classes: primary or chain-breaking antioxidants and secondary or preventative antioxidants. Chain-breaking antioxidants act with this mechanism shown here. We see lipid radicals here, or lipid peroxide radicals. And of course, if this chain goes on, then the lipid molecule is oxidized, or the macromolecule like DNA or protein is oxidized. But when the antioxidant is present in the system, then antioxidant sacrifices itself and prevents this chain-breaking mechanism. In other words, it breaks the chain. It breaks the chain. And therefore, we call these types of antioxidants chain-breaking antioxidants, and these types of antioxidants are being measured in our lab primarily. A second mechanism of antioxidant action is prevention of Fenton-type reactions. What is a Fenton-type reaction? Transition metal ions like iron and copper give rise to reactive species in the presence of oxygen or hydrogen peroxide. And of course, when the antioxidant is present in the system, it combines with iron or copper. It chelates, for example. It forms a covalent bond with these transition ions, and therefore it prevents these. It prevents the emergence. It prevents the formation of these radical species here. The chemical diversity of antioxidants, relative abundance of their glucoses and isomers, makes it difficult to separate and quantify antioxidants from the food or biological matrices, where their combined action may be more relevant. In other words, with antioxidant capacity measurements. Therefore, it is desirable to measure the total antioxidant activity or capacity level directly from, rather than measure these antioxidants individually, the total or health beneficial effect. Antioxidant assays, as I have said before, is electron transfer-based assays and hydrogen atom transfer-based assays. Donates an electron or a hydrogen atom to a reactive species in order to quench it. Measuring the antioxidant capacity levels of biological foods and foods is carried out for the diagnosis and treatment and for controlling variations within or between products. In 2004, we launched a new antioxidant method, a total antioxidant capacity measurement method, which we called Cupric Reducing Antioxidant Capacity Measurement, abbreviated as the Cupric Method. And this method has been very popular in world research centers of food and antioxidant research. It has retrieved about 1,800 citations within the 10 years. And also it has been patented in the USA. There are many types of antioxidants, as you can see in this broad diagram. There are enzymatic antioxidants like superoxide dismutase, catalase, glutathione peroxidase, etc. And there are non-enzymatic antioxidants like carotenoids, low molecular weight antioxidants, for example, the glutathione, which is a very famous thiol-type antioxidant in the body, uric acid, bilirubin, and so forth, and vitamins like vitamin C, vitamin E, organosulfur compounds, etc. And polyphenols are divided into two classes, flavonoids and phenolic acids. We can see the structural formulas, but I will not go into the details. And these are the structural formulas of flavonoids as well. These are quite technical for some audience. Requirements for a high antioxidant capacity. This is very important because when you devise a new analytical method, then you have to pay attention to these structure-activity relationships. For example, quercetin is a very famous antioxidant, basically found in apples and some other plant foods. The structural characteristics, you can see here the two hydroxyl substituents in the B ring of flavonoid, the double bond here, and this function here. These are very important structural requirements for a high antioxidant capacity or activity. And of course, when you devise an analytical method, you have to sort, you have to make an order of antioxidants with respect to their strength, antioxidant strength. And of course, quercetin should come at the top, and then some phenolic acids, and then coumaric acid and glutathione, etc. So there is a sequence of analytical, there's a sequence of antioxidant power, and of course, your method should pay attention to these requirements. And our method of Cupric method pays attention to these requirements in that it shows a very high antioxidant capacity for quercetin and similar molecules, which has an overall conjugated structure, which makes an electron transfer easy. Electron transfer-based assays using a fluorophore or chromophore have this type of reaction where you use a probe, and the probe receives an electron from the antioxidant and is itself reduced to itself is converted to a reduced type of probe, and the antioxidant is oxidized, of course, in this reaction. And this reduced probe should have different spectral characteristics than the main molecule. Therefore, the reduced and oxidized probes should have different spectroscopic characteristics like fluorescence or phosphorescence or absorbance, molecular absorbance. Electron transfer-based assays, all of them are spectrophotometric or fluorometric, include FOLINFRAP, ferricyanide, and the Cupric that we launched in 2004. And also there are some radical species. For example, this ABTS is a radical species, and it is being sold in the market, but it's rather unstable. You make it stable by oxidizing with persulfate or manganese dioxide or hydrogen peroxide. And in this oxidized form, it can react with an antioxidant. Of course, the antioxidant reduces this radical species, and therefore the color is quenched. So you can measure the color loss within a certain period of time, and you can get an idea of the antioxidant power. There are other methods like FRAP. For example, this is an iron complex, complex to tripyridyl triazine, and when it receives an electron from the antioxidant, it is reduced to the ferrous state or iron 2 state, and it's highly colored. Therefore, you can measure the color difference. The DPPH is also a stable radical being sold in the market. It is colored, but when it receives an electron from the antioxidant, it fades away, and therefore there is a discolorization. And you can measure this discolorization at a specific wavelength of 520 nanometers, and you can get an idea of the antioxidant power as well. There is ferricyanide method. Ferricyanide is reduced to ferrocyanide when it receives an electron from the antioxidant. And when you add an iron 3 species here, the Prussian blue kind of formation appears, and therefore this is highly colored, and therefore you can get an idea of the antioxidant power of this phenolic species. There is Folin assay, which has been developed in 1927 for proteins, but later on adapted to antioxidant measurements. It's also a phosphomolybdotungstate type of heteropolluanion. When it receives an electron from the antioxidant, it is converted into a highly blue complex. And this is the contribution that we have made in our lab in 2004. This is the Cupric method. Here you can see copper 2 ion chelated to 2 neocuproene molecules, and when it receives an electron from the antioxidant, it is converted into the copper 1 or cuprose state, and it is highly colored because of the charge transfer complexation here. Charge transfer complex, and it highly absorbs at 415 nanometers, and you can measure the absorbance, and you can correlate with the antioxidant concentration. Of course, the copper 1 state is highly stabilized in the presence of neocuprine. in preference to copper 2 state, and therefore copper 2, copper 1 redox potential of 0.17 volts is raised to 0.60 volts, a high rise in redox potential, because this copper 1 state is being stabilized here, and this makes this type of antioxidant reaction very specific for some phenolic antioxidants and some very important antioxidants in the body, physiological antioxidants, because most physiological antioxidants and most phenolic antioxidants have the range, the potential range between 0.4 and 0.6 volts, and this reagent is powerful enough to oxidize all of them. And therefore, for many types of antioxidants, very diverse type of antioxidants, our reagent can oxidize all of them to give meaningful results. The method is very simple. You can simply mix a copper 2 chloride solution with a neocuproene alcoholic solution and an ammonium acetate buffer, and then react it at pH 7 with the antioxidant complex sample. And of course, the color develops at 450 nanometers within 30 minutes. Most antioxidants are oxidized within this protocol time. For some flavonoid glycosids to exert their maximal antioxidant power, you can reflux them in 1.2 molar HCl containing 50% methanol solution, so as to get their maximal antioxidant power. Cupric method can also be applied to human fluids, meaning that you can measure, for example, plasma antioxidant level or serum antioxidant level, and ascorbic acid, alpha-tocopherol, glutathione, and similar small molecule non-enzymatic antioxidants in the body can be measured. And what is the advantage of this? Of course, for some oxidative stress-originated diseases, you can measure the antioxidant level of serum or some cellular fluids, and you can get an idea of the disease. For example, you can use it in the detection or in the follow-up or in the treatment of diseases in various stages, just by looking at the antioxidant power of plasma or cellular intercellular fluids. You can measure ascorbic acid individually with this method. I will not go into the technical details, but I will give the headlines. You can measure hydrophilic and lipophilic antioxidants in the same solution. That is a very important advantage that cannot be obtained with other antioxidant activity assays, because, for example, some oil-soluble antioxidants like BHA, BHT, and TBHQ can be measured together with very highly soluble antioxidants like ascorbic acid and glutathione in the same solution by using a trick, by using this type of polysaccharide, because this type of polysaccharide forms inclusion complexes with lipophilic and hydrophilic antioxidants. So you can measure them together in the same solution, which is a very important high advantage. You can measure hydroxyl radicals. Hydroxyl radicals scavenging power of antioxidants with this method. Of course, you have to make some modifications, which I will not go into the details here. And also, you can measure superoxide anion radicals scavenging activity of antioxidants by making spectral difference between the probe and the end product. You can measure hydrogen peroxide, which is very important reactive species for the human body. And also you can measure catalase. Catalase is a hydrogen peroxide annihilating enzyme. You can measure it indirectly with the Cupric method. You can measure protein thiols, which is also a very high advantage that can be achieved with the Cupric reagent, but not with the other antioxidant assays, because protein thiols are usually being ignored in the assays. On the other hand, protein thiols are major reactive antioxidants that can fight with diseases, for example, that can fight with various diseases and infections. And of course, measurement of protein thiols is a very important matter in food antioxidant analytical chemistry. And this can be achieved by the Cupric method. We also developed a Cupric sensor, like a pH paper. When you dip a pH paper into a solution, you immediately can measure the pH of the solution. In this manner, we can dip this Cupric antioxidant sensor, which is a Nafion sensor impregnated with a Cupric reagent, and you can measure the antioxidant level of the complex fluid directly on the sensor membrane, like a pH paper. This has also unification with, this is also a possibility of unification with HPLC, meaning that you can get relevant information from HPLC in the first column, and when you react the column output with a Cupric reagent in a reaction column, you can get secondary information just for the antioxidants, because the Cupric reagent only reacts with the antioxidants, and it is very selective. For example, this is a classical chromatogram you can get from HPLC instrument, and this is the post-column Cupric method. Here, only the antioxidants reply. You can get a response only from the antioxidants in the second chromatogram, but not from the usual molecules. Therefore, you can make this method very selective by combining it with HPLC. Okay, this is the Oxford Biomedical Research kit that is being used in medical faculties. There are many applications for food plants. I will not go into the details. We also have a food antioxidant measurement center in Istanbul University, which has been active for the last 2 years, and we can analyze all sorts of antioxidants and food products here. This is my research group, you can see, and thank you.
Thank you for your great presentation. Do you have any comments or questions? Yeah, Professor. No, yeah.
Professor Aras.
Yeah, Aras.
Not working.
Thank you very much for this wonderful presentation. I'm just wondering what other elements could affect, like copper, for instance, cobalt. I'm sure that you tested many elements. Which other elements that could be in the same level?
That's a very good question. All redox active elements, of course, when you have an iron 2, it also make a reduction. But you can mask certain elements as but when you are making a scavenging assay, for example, hydroxide radical scavenging or superoxide radical scavenging assay, then you have to exclude those elements because these types of elements make Fenton type reactions come to the stage. Of course, when these transition metals ions are present and you're producing some reactive species with hydrogen peroxide, then of course they affect the formation of these reactive species. And therefore, but most alkaline earth metals, they do not interfere with the reagent. But you can mask it with the EDTA and that kind of thing.
Okay, thank you.
Thank you. Yeah. One more question.
Yes, I have two questions, but I hope you won't ask question to me when I am there, okay? But the first one, yesterday, Dr. Esra has mentioned that when there is a stress and plants increase their antioxidant activity, do you have any data, because today's subject is more on the effect of climate, so do you have any data if any change has occurred because of the climate change, any oxidation potential increased or decreased in the plants?
Yes, very good question. But we don't have too many applications from plant science. We are usually developing new analytical methodology, and some other practitioners use these methods. For example, Esra Çapanoğlu from Food Engineering Department of Istanbul Technical University. But we ourselves have made some measurements on Malatya apricot. And we have seen that Malatya apricot has a slightly higher, about 10% or 15% higher antioxidant activity than, for example, California or USA apricots. We attribute it to the hard climate conditions in Malatya. Because we thought, why should it have higher antioxidant activity? And we came to this solution, but of course we are not sure. That is one possible scenario.
Right. Sorry, the second question was, you're talking about antioxidant power in the blood system.
Yeah.
How do you correlate it? Is it increasing or decreasing depending on some diseases or cancer patients and so on?
Yeah, that's a very good question also. For example, for acute lymphoblastic leukemia and some cardiovascular diseases, it drops. But in order to correlate it, you have to take one individual, not all the population, because some people have very divergent antioxidant levels, and therefore you cannot extend your results to the whole population, but for one specific person. Like, for example, in cancer treatment, you know that there are some anti-tumor tumor markers. And if a given individual increases its tumor marker, then it means that some type of cancer is getting back or is being regenerated in that body. So for a specific individual, it has a meaning. But for the whole population, unfortunately, it does not have too much meaning currently, but it can be, of course, discovered in the near future. And in some parts of, for example, hyperuricemia. Hyperuricemia means your kidneys cannot function, and therefore the uric acid levels rise. And of course, this is not a healthy rise. This is not a healthy rise of antioxidant level. There are some healthy rises of antioxidant level, but of course, hyperuricemia is an exception. It is not good in hyperuricemia, the antioxidant rise.
Can you differentiate these with others?
Of course, you can measure uric acid separately. Yeah, for example, in our method, you can apply the Cupric method. Cupric method does not differentiate between uric acid and bilirubin and glutathione and so on, but then you add an enzyme which is specific for uric acid. That enzyme annihilates uric acid component, and the other components are measured in the second place, and therefore you can get the difference. You can get the difference.
Thank you.
Thank you.
Please. Thank you, Professor. I have just two questions. The one, you made a very wonderful presentation. And my first question is this: what sorts of mechanism you have in your university with the industries?
With the industries?
Yeah, to provide the services. My second question is, do the industry support research in your university?
Unfortunately, I cannot give a very positive answer to these types of questions because the industry, industrial-based research is not highly developed in our country, like in the USA, because of the capitalism system. It's basically based on state capitalism. I mean, the state finances all these researchers, and therefore the universities and some government-owned institutions like TÜBİTAK, Turkish Scientific and Technical Research Council, and the main research is being carried out in the government institutions, and of course, some private institutions like the food sector probably supports certain projects, but not to a high extent. Not to a high extent.
Okay, sir. My question is, you have mentioned 6 different methods for antioxidant testing, but in our laboratory we use 4 different methods, and the DPPS method and ABTS method, they are more popular in our laboratory, and they are very expensive. Yeah. And the Cupric method is a cheaper one. But you mentioned here that this one is the best one. Do you think that this is, this can be used for all types of antioxidants.
Yeah. Very good question. Yeah, DPPH, for example, is very sensitive to light and air oxygen. Especially DPPH is very sensitive to light and air oxygen, but the Cupric method is not at all sensitive to light, not at all sensitive to air oxygen, meaning that it is not affected by air oxygen, which is a very important advantage because in the lab you cannot exclude oxygen from the system. This is a very important advantage over DPPH method. And of course, some phenolic acids are not being efficiently measured by the DPPH method. This is a third advantage. ABTS method is the only competent method that can really compete with Cupric, because ABTS measures both hydrophilic and lipophilic antioxidants, and it can be applied to human fluids as well. And therefore, ABTS is our unique competitor or rival. But ABTS, I think, has a very high Trolox equivalent antioxidant capacity for thiol-type antioxidants. For thiols, it has a very high level for thiols, and it is not realistic. It is not realistic at all, because thiols are normally oxidized in the body reversibly to disulfides. Thiols are oxidized to disulfides in the body, and it is a reversible reaction. And in the Cupric reaction, they are converted to disulfides. But in the ABTS reaction, they are oxidized to higher levels, like sulfanic and sulfinic acids, which is not realistic at all, which is not realistic. Mm-hmm. Our method is more realistic than ABTS in its oxidation level for thiols.
Okay, thank you, sir.
Okay. Thank you. Professor Apak. Where is my partner? Professor Amin, come here. Thank you. Okay. Second speaker, Professor Dr. Faruk Bozoğlu. He's from Middle East food engineering. He has a lot of collaboration, such as University of Wyoming, and he has a major. Please.
Well, thank you very much for the invitation and my speech that I will give in here. And I'd like to thank my professor, dear professor. As we see with our today's talk will be mainly on the climate and effect of climate on food resources. My topic will be a little different. It will be more on security, which means that you can produce food, but your food, if it's not safe, contaminated with chemicals or microorganisms, and it is not fit for the human consumptions, that may cause big problems later on. And humans rely on the sustainability of the ecosystems. If anything changes in the ecosystem, we get the effects, the domino effects at the end that will affect even our health, our children, and our future. Now, if you look to the ecosystems, we define them as a network of individuals that arrange into self-organized and complex systems, and several levels of bigger systems. They all constitute systems of smaller systems within them. And ecosystems create biophysical feedback between biotic and abiotic components of an environment that generates and regulates the geochemical cycles on the planet. Unfortunately, ecosystems have been disrupted and even destroyed by natural disasters, such as fires, floods, storms, and volcanic eruptions. Of course, human activities have also contributed to the disturbance of many ecosystems. And these disruptions of ecosystems, of course, will have a great impact on health in a variety of ways through complex pathways. And these pathways are experienced are determined by the degree to which local populations depend on ecosystem services and factors such as poverty, which affect vulnerability to changes in elements like access to food and water. We have been speaking about the rise of temperature, mean global temperatures. We have seen that increase since 1850 because of uncontrollable increase in the greenhouses in the atmosphere, and the main causes is the burning of fossil fuels. Of course, these changes are all interrelated. A climate change is triggered by desertification and land degradation that we see now, the rainforest in Brazil and other parts of the world. Of course, the ozone depletion, increase of carbon dioxide, that all increase the changes that affects human health, especially from agro-ecosystem productivity decreases. Now, they have separated this effect according to the years and future increase in the temperature. On the right side, you see the figure, the future increase in the temperature and the span of the time. Now, we have 5 risk groups. The most risky is the unique and threatened systems, 1 or 2 systems, but the least one is the risk of irreversible and large-scale abrupt transitions. The first 20-25 years, we see a risk on the unique threatened systems, but at longer time, around 2100, which is 70 years later on that, the risk for irreversible large-scale and abrupt transition is increased because the foreseen temperature increase is around 5 to 6 degrees compared to today. Of course, this will have a stress on ecological systems. Now, for animals, if any changes in ecological systems occurs, what they do, they migrate, or they lower population, or even they change their eating habits. So they try to survive in this system. Now, humans have more pathways, like social mechanism to adapt to climate change and mitigate ecological stresses. Besides migration, we have warfare, unfortunately, economic changes, innovations, trade, and peaceful resource distribution. However, when the speed of human innovation and its transfer were not fast enough to keep the pace with rapid ecological change, this is true that famine and disease become difficult to avoid. And today we see that everywhere in the world. Finally, human social development in the form of international and national institutions is not strong enough to buffer the tensions caused by food resource scarcity. Now, the first affected ecosystem is the marine system, and the changing climate has been linked to a wide range of impacts on marine ecosystems, either directly, which is the increase of sea temperature, or indirectly through impacts on the seasonality, distribution, and abundance of species. The impacts of future climate trends on marine ecosystems are difficult to predict due to a number of uncertainties, because we don't have any data to make scenarios for the future greenhouse gas emissions. Okay, 2 facts. One is the increase of carbon dioxide that will increase acidification. Because of that, it will reduce the carbon dioxide. It will change the food web. The second one, because of the increase of the temperature, air temperature, rainfall changes, land thaw and ice melt, increase meltwater, change the thermal expansion, salinity, and type of nutrient that will affect the real ecosystem of the marine world. But of course, the major impact is in agriculture because the largest population of the world depends on the agricultural sources. So the productivity of agriculture productivity will be changed. It is very sensitive to climate variability and weather extremes such as drought, floods, and severe storms. The forces that shape our climate are also critical to farm productivity. Now, even if we look to a small part of the European countries, you see the climate change shows very strong differences from one part to another one. Although on the northern part, we see growing season increasing, crop potential increasing, but it will affect the increase of pests, storms, and increase the lake levels. If we come to the south part of the Europe, like Spain, Italy, and even Turkey in this one, there will be less change in the temperature, but always a drought risk. Crop yield decreased and suitable crop area decreases. Only in a part that we see, like France, some part of Germany and England, although there will be floods and sea levels, they increase their crop and the range of crops in this area. Now, however, if we look to the developing countries, climate change will cause yield declines for the most important crops, like rice and wheat and so on. South Asia will be particularly hit hard. Climate change will have varying effects on irrigated yields across regions, but irrigated yields for all crops in South Asia will experience large declines that you can see from the figures. The red ones are the maybe most hardly hit parts of the world that have real declines. Now, real declines can be overcome by buying the food from other sources, but of course this affects the food prices. So the climate change will result in additional price increases for the most important agricultural crops like rice, wheat, maize. So they will increase the feed prices, and at the end you will have high meat prices that we see in Turkey today. As a result, climate change will reduce the growth in meat consumption slightly and cause a more substantial fall in cereals consumption. Now, this figure gives you basic approaches in 2000, 2050, 2052 of them. One is fertilized one, carbonate fertilized one, 250, the other one non-fertilized. The prices of major grains as US dollar per metric ton. Now rice will increase at least 3 times, wheat maybe more than 3 times, and other grains also all increase in the prices. And livestock products also, except eggs, the prices are increased not as the prices of the grains, but they will go a little bit higher in 2050. Now, what happens when the food prices increase? You remember when the food prices increases suddenly at 2007 and second quarter of 2008, a global crisis started, resulting political and economical instability and social unrest in both poor and some developed countries, which is important. Now, if you look at the FAO food price index and commodity price index, there has been an extent increase until 2007, then decrease in 2008, again started to increase in 2010. Now, the recent price indexes, we see that there has been a steady decline in the food prices index. And people usually correlate that with oil prices. Okay, when oil prices increases, food prices index increases. However, if you look at in Turkish way, in Turkey we see the continuing of rises of the prices, implying that large price increases in Turkish market stem not only from unfavorable weather conditions, because weather conditions plus the decrease of the petroleum should affect that. But what we see, the officials in the country have been claiming that it was because of weather conditions, but people believe that other factors such as unfair practices of intermediaries and lack of unity among producers also will affect. So we should not only blame the change of climate, so there should be some other ways of fighting against these prices. Now, you see on the left one how we see the decrease, but in Turkish market we see always an increase of the consumer price index. Now, if the cost of food increases, now, of course, it affects as an impact in the reduction of reduced calorie intake, especially for the children, and increased childhood malnutrition. Now, when we come back to the food security, as we said, agriculture is extremely vulnerable to climate change. Higher temperatures reduce yields of desirable crops. At the same time, encourage the unwanted weed and pest proliferation. Okay, so this is a real scenario. So changes in precipitation patterns increase the likelihood of short-run crop failures and long-run production declines. And we see from this figure that the main part of the world which is hit by these crop yield declines in 2050 will be the North Africa, Middle East, and South Asia. And the unnourished children will be increasing tremendously from, for example, in South Asia from 52 million to 59, in sub-Saharan 42 to 52 millions. As long as the economic returns justify the costs, people can now create artificial microclimates, breed plants and animals with desired characteristics, enhance soil quality, and control the flow of water, so to increase the yield. Now, the point is that you can increase the yield, but how about the effect of this on human health? Researchers believe climate change will have widespread implications for food production, food security, and also food safety. For example, seafood safety is a problem because toxic algal blooms are increasing, deadly Vibrio are increasing, and methylation of mercury is a hazard to human health. So this risk will impair food and feed safety. In particular, production of mycotoxins, marine biotoxins, and foodborne pathogens. Epidemics of foodborne illnesses linked to fresh produce increase in absolute number in the proportion of total food-linked outbreaks with a known etiological agent. Especially very specific pathogens, they cause epidemics of enteric illnesses like Salmonella, pathogenic E. coli, Shigella, Campylobacter, Listeria, Staphylococcus yersinia, and Bacillus cereus. And Salmonella enterica, which is enteric pathogen, is the most frequent etiological agent that we see increase that cause 48% of such outbreaks. Of particular concern, there is one microorganism pathogen which is very important, which is the multi-drug resistant strains of Salmonella enterica. And pathogenic E. coli is the second most important causal agent outbreaks from fresh produce that may even cause the loss of kidneys, especially in children. As a conclusion, projection for 21st century shows that if global warming increases, it will accelerate stronger storm systems. As we seen yesterday in Istanbul, there was not too much, but still extreme precipitation and dry spells and rising sea levels as the primary symptoms. In wealthy nations as well as in poor ones, consumers express alarm about fast rising prices that will, of course, translate into unrest and political crisis. Some higher temperature in the sea will increase some problems in marine organisms. For example, they will first off migrate to another parts of the world. Now in Mediterranean Sea, we are seeing a lot of different fish that has not been seen for several years. Marine biotoxins and problems from mussels for food productions may have harmful effects. And if climate continues to move toward extreme temperatures due to drought and floods, we will have food to be more expensive and uncertain. Of course, increasing food research probably would be a wise precautionary move against this one. And we have seen these changes as an example, harmful crops as recent severe drought in Russia and China, and floods in Australia, India, Pakistan, and some parts of Europe. Now, today, the world is a place of uneven development, unsustainable use of natural resources, worsening impact of climate change, and continued poverty and, unfortunately, malnutrition. Poor food quality and diets are partly responsible for the increase of chronic diseases like obesity, heart disease, and foodborne illnesses. Okay, if you see the impact of malnutrition, we see reduced low mood, weight loss, muscle wasting, confusion. Everything is related because of the lack of the foods. Thank you.
Thank you.
And thank you, our workshop chair, Professor Kazım Şahin, for being the chair for this session. Now the session is over.